Oh, so you mean saying thank you very much for the opportunity to give a talk about templates and this wonderful theorem. So you are very welcome. Please.
Thank you. Thank you for your inviting.
Okay, so you may begin.
Oh,
You may
okay.
start.
I want to use the PowerPoint, so I will
Yeah,
share my.
is everything okay with the demonstration? Try, please.
Okay. Uh, can you see the PowerPoint?
We see
Yeah, yes.
Oh,
this is
okay, okay,
PowerPoint. We see slides.
okay, okay.
Hello.
Oh, Antoine, hello. Hello. We just starting.
Great.
Hello. Shall I begin?
Yes, you.
Okay.
Hello, Antoine.
First, I think it's better for me to record
Yes,
some
of course.
definitions and
If you will explain as slow as you can, it would be wonderful because we do not have real say time limitation. And I always say that if you explain something for specialists, you should think that they understand nothing, and explain everything. Otherwise, they will not understand.
okay. So I will begin with ROA's construction. First, I think he defined a convex body which is different with the convex body considered by Schmidt and Zumira. In Schmidt and Zumira's convex body, I think the volume is a constant, and the convex body in ROA's paper, the convex body, the volume of convex body have a growth rate of 1. Here is the definition of the convex body called CU with respect to the time t, and U is a given unit vector in Rn. For each J, we can consider the successive minima corresponding with this convex body. And for convenient here, I want to choose the map LU, which is the log of the successive minima. It can be defined as for each J, L is the smallest real number L such that this convex body contains at least J linear independent points of Zn. So we can write this LU function below here. And for each J, we can find that this LUJ is a continuous and piecewise linear function with slope 0 and 1. And this map LU takes values in a monotone increasing n-tuples of real numbers because we know that LU1 will less or equal than LU2 will less or equal than Ln. So the values so the LU function take values in this special set. To understand this LU map more clearly, we can define for each integer vector in Zn, we can define the lambda x. Lambda x is the smallest number lambda, such that x is contained in this convex body. So for convenient, we also consider the log of lambda x function, which is lxt here. because this convex body, we know it exactly, so we can calculate Lx t by the maximum of log of x and t plus log of u dot x. This function, the graph of this function is very clear. When t equals log x minus log u dot t. So in the left side, it is a constant function. It's just a line with slope 0, and in the right side, it has slope 1. Then for each t, we can use a basis of Zn to fit the map LUT. Here, for each t, we can choose a basis, but because LU is piecewise linear function, so we can choose a sequence of basis vectors of Zn such that in a linear segment, we can use one basis, and from step 1 to step 2, we change the basis. We change the basis vector xi to fit the LU map. Then Rua defines the rigid N system with mesh delta. Here, he first defined a canvas with mesh delta, which is the I think it's the nodes information encoding in the rigid N systems. The definition here is for each I, it is n numbers vector, which is AI, and the coordinate of AI is a strictly increasing sequence of positive integers with which is the multiple of delta.
So difference between every ace is a multiple of delta.
Yes.
Yes.
And the second condition describes the index of this convex Ki and Li. Ki means if we consider a rigid N system, maybe I will show it first. Such as we have this rigid N system. Ki means in AKI, the left side of AKI have slope 0, and the right-hand side of AKI has slope 1, such as in T1 equals 22, K1 is 2, and the Li means in the left side of ALI have slope 0, have the slope 1, and in the right-hand side have slope 0. For example, in T1, L1 equals 3. So it is the definition of Ki and Li. So I will go back to this definition. And in condition 2, he claims that for each I is larger than 1, Ki will less than Li. It's a restriction of the rigid N system. And the condition 3 means in each step, we from step I to step I plus 1, only one nodes have changed. Corresponding to the rigid N system, it means in each linear segment, there is only one function with slope 1 and n minus 1 function with slope 0. here is the definition of rigid N system with mesh delta.
Okay,
and
so you simply connect this
yes, this convex
nodes by constant or points, constant function and one function with coefficient plus one.
Yes, yes.
So you connect the point number ki with the point number li plus 1, basically each time.
Yes.
This corresponds to original ROAS setting.
Yeah.
Yes.
For one linear form.
Yes.
Or dually simultaneous approximation. Yes.
And
yes.
So can you show the graph? Maybe it will be more clear why li should be bigger than ki. That's what I don't understand. I understand how li plus 1 should be bigger than ki. But why should li be bigger than ki?
Because
or maybe it's just a restriction that we put.
Yes, I think when we consider the graph of LU, is the log of successive minima, it will satisfy this condition. So and in the construction of LU, this condition is very crucial.
Oh, so you need it for later, for the bijection between these and matrices.
Yes.
Oh, okay, or linear forms. Okay.
Yes.
So here, just to draw a picture, what we naturally see here is that li plus 1 is bigger than ki and nothing else.
Yes.
But later, okay.
And
we see that Li is on this picture. Li is also bigger, and this is one of the usual conditions that is sometimes called valley peak condition.
Yes, we are more familiar with just valley peak condition. So that here, when we have when the derivative is not defined, then the we have this value peak. Okay.
Okay, I will continue.
Yes.
And I think in Roa's paper there are two parts. In the first section, Roa established the following theorem for a given unrigid system with large mesh delta, which is we defined before. There will exist a unique vector U such that the map defined by LU is bounded difference with the rigid N system. Yeah, it is the first part, and the proof is, I think, using the construction. And in the second part, he defined a more general class of functions he called the N-gamma system. N-gamma system satisfies the following 5 conditions.
Sorry, can we have a look at the previous one for a second?
Okay.
So is in his proof, I guess I know the answer, but just to check, is in his proof LU minus P bounded after we fix U, or is there any uniform bound for all
yes,
U?
it's a uniform bound given by the dimension N.
It is even it doesn't depend even on delta, isn't it?
Yes, it doesn't depend on delta. It just depends on N, the dimension N.
Okay, because I'm just trying to compare with DFSU, which I'm more familiar with.
Oh, I actually I don't know the arrow in DFSU. Does they give a uniform bound or?
They do not refer to the uniform bound, but I'm recalling the proof now, and I guess what they prove really gives the uniform
Okay.
bound. But in all the formulation, they say that just there exists that they
Okay.
have this finite
Yeah,
perturbation definition, and it
Mm-hmm.
does not explicitly give the bound.
Okay.
I have
In the
two.
last
Okay,
in the
okay.
last version of DFSU, they have a uniform. They claim they have a uniform bound, but it's only the very last published version. Before that, it was claimed it was not. So
Oh yeah, I read
that's
the
what I
archive
can
version.
Okay,
I read the archive version.
Oh,
say.
I also want to ask several general questions. First of all, Vasya said some time ago that it is not possible to extract from DFSU an simple existence proof without families of templates. Isn't it?
Oh, so
Is it so?
sorry, I
This is
didn't.
this is question probably to Vasya.
What do you mean by families of templates?
So there is a theorem. They claim that if there is a family of templates satisfying something, then the number of the set of matrices for which this family happens has something, and then something with Hausdorff dimension.
Yes.
They do not claim that if they have just a template which satisfies their condition, say including peak value condition, then there exists a vector, a matrix which is LU minus P is bounded.
No. They do claim it, but the difference is they need the families, especially for the fact that their families are what they call closed under finite perturbations, and
Yes,
they
yes.
compare templates with this minima function also up to finite perturbation. So this is an essential condition because we want a bijection of the function with the whole class, not the function with a single template.
Informal question. It is not possible to extract immediately to extract a proof from the FSU for a single template, isn't it?
In the direction that if we have a template, then there is a matrix.
Yes.
As I understand, it's not possible. Yes.
Yes. So
I do not. I only know the place where they refer to Roy and then refer to their correspondence between Roy and their language.
And they do not give explicit proof of this statement for a single template.
Well, maybe they changed it somewhere. Maybe one of the million versions contains something that I haven't seen, but at least the one that I was reading, no.
And so you did not look into the final version in advances.
I don't remember, but most of the time I just printed some version and read it on paper because it was more convenient.
Maybe
and
Antoine,
it was before. It probably was before it was published in advances.
Maybe Antoine knows if there is an explicit proof of this simpler existence statement.
Well, I don't remember seeing it. And
I
I'm
looked
like
at previous
Vasya.
versions.
I also looked at some versions, and I need to print it on paper because it's horrible otherwise, and maybe I missed something at some point.
So do I. I was looking for this statement in previous version, and I did not find it. But for now, I'm sorry, a question to Antoine. But for our purpose, formally, we need a family of templates. I mean, for our paper.
Yes.
So for our paper, formally, it follows from DFSU.
Yes.
Because we need a family of templates, because in fact our examples have positive Hausdorff dimension.
Yes.
Okay. Well, then another question to you mean. So is it true that this theorem, which is now on the screen, and the next one is simply in some sense a limit version of this theorem. You will speak. The next theorem is also due to Roy. Yes.
Yes.
Okay. And then I would ask you when it happened that you need some additional conditions. Please let us know so immediately, okay? Because it is very interesting.
Additional.
You said
Sorry.
in the some time ago that do you need some additional condition to prove for 2 by 2 matrices?
Yes.
Okay. Wonderful. Let's continue. Wonderful.
Okay. In the second part of Roy's proof, he defined a more general class of functions he called the N-gamma system, and then he used the next theorem to the next theorem states that for a general N-gamma system, he can use the previous rigid N system to approximate with a bounded difference. Here is
This is wonderful statement. All the constants are explicit.
Yes. And this I think this constant will depend on delta. Here delta is the rigid N system's mesh. So if we
This
combine,
is related on mesh.
yes, and if we combine this the theorem 1 and theorem 2, I think he proves that for a general N-gamma system, he can find a unique vector u in Rn such that pt minus lu is bounded by some constant. So that was Roa's proof in Roa's statement in his paper, and in another paper of Roa, he defined a general N system, and he also showed that for this general N system, he can construct a unique vector u, and such that Lu minus P is bounded difference. And in my work, I only generalize the first part of Roa's paper, which is I defined a convex with mesh in 2 by 2 matrix case, and show that there exists some there exists a matrix U such that Lu minus P is bounded, and for the
one question to everybody. Is it true that so of course the main technical theorem is just the theorem which is on the screen now with mesh, but is it true that if we need to apply this theorem to have existence results, we can simply we have, for instance, a special template, and we can simply approximate it by a template of the form of theorem of this theorem with mesh. I think there is no problem to consider a little bit more different template, which is close to our template, which satisfies this mesh property, isn't it? So the main difficulty is to prove this theorem with mesh. I think this is the most important. Yes.
Yes, I agree with that.
Okay, wonderful. So you mean you did the main part of the work?
okay, because the second part, I think in Roa's paper, it looks very complicated, so I didn't
Too complicated, too cumbersome, too formal. Yes.
yes.
But the most important, if we have a statement with mesh, we are able to apply it. So it is the main thing.
Okay.
Of course, you did not speak about gluing the functions, because now we like to glue functions and to consider functions not with coefficient 1, but with some other coefficients. But it is not of importance. The most important thing is this discrete result. Okay, wonderful.
Okay. So next I will introduce the rigid 2 times 2 system in a matrix case. First, I think we should define the convex bodies in this case. So we let A is a matrix, 2 by 2 matrix, and U is a 2-dimensional subspace in R4 generated by these 2 vectors. And this 2 vector is determined by this matrix. And we let W is the orthogonal subspace of U. So we can have this convex body defined by the 2-dimensional subspace U, which is similar with the with the vector case. And we use the same idea to denote the LU function. For each J, LJ means the smallest number L, such that this convex body contains at least J linearly independent points in Z4. So we use the so next we will define the Lx function according to previous argument. This function can be defined by the smallest real number L, such that X is contained in this convex body.
Oh.
So the function Lx looks the same with the previous one. Functions, one is log x, the projection to the u delta x, which is can be generalized by this projection map. And the so for each
Something seems to be wrong with the sound.
Yes. Well, something wrong with the connection.
So it's probably, yeah, it looks like Yuming's connection.
You mean, I think now it is better to switch off. Maybe it is reasonable to switch off video. It will work better.
Yeah, because we don't hear almost anything.
Yes, some I see some problems with connection. Maybe. Something not very good. So you think, Vasha, you think it is Yuming's?
I think it's Yuming's because we hear each other well.
Yes, I think it's Yuming because I hear you very well.
I agree.
I hear only qua.
J
Yes, this becomes international.
will equals to
Does anyone
LJ.
know qua
So we
on any other
can
language?
a basis of a vector.
Oh, it becomes better. Oh, you mean I think something doesn't work proper.
She's disconnected now. She's disconnected now.
Yes. Okay, I think to switch on, or you mean hello, you're again here. Wonderful. I think it is a good solution. It is a good solution to close and to open Zoom again. It will work better, I think. Because
Okay,
the last few minutes we did not hear anything, just qua.
Oh, sorry.
No problem. It is on probably you may switch off video, then it will be better.
Okay.
Okay, now it's okay. Yes, isn't it?
Oh, okay.
I think now it's okay.
I think I can make a comment. I just opened the advances version of the paper.
Yes.
And they have this theorem 4.2, which is basically part 2 is that for any template there exists a matrix.
Yes.
And they now say in case m equal to 1, this theorem follows from ρ.
And in general case?
And then they say corollary 4.7. Wait. In 56, and 56 is probably also ρ. Yes, also from ρ. They still say that it follows from ρ.
In dimension 1?
No, they, as I understand,
for matrices,
they claim that it follows for arbitrary m and n. Or wait, it's not clear. Let me.
Okay.
They say in case m equal to 1, theorem 4.2 follows from 55 theorem 1.3, which is ρ. And then they say CF 56 corollary 4.7 for part 2. And it's not clear. This last statement refers to m equal to 1 or to general m.
But Roa claims that
yes, I know.
that he cannot prove theorem for arbitrary matrices, for 2x2 matrices.
Yes.
So they and in DFSU they do not, in the last version they do not have explanation of just existence result, isn't it? Vasi is a specialist now.
I do not find it, at least. But
in previous version, I myself did not find. But it was few years ago when I was before then I was in Israel. Okay, let us continue. Wonderful. The connection is recovered, everything is fine, and Yuming may continue. So please continue.
Okay. I will begin with the first part. So if A is a 2x2 matrix and U is a two-dimensional subspace generated by two vectors x1, x2, which is determined by the matrix A, and let W is the orthogonal subspace of U, then we can define the convex body CU. It looks the same with the previous one because the previous one, the second part is U dot X. The norm of U dot X will less or equal than e to the power of T. So in two-dimensional case, we use the projection function. So here is the definition of convex bodies, and so it's natural to define the Li function with respect to this convex body. Sorry. Next, we still define the function of Lx. Lx is the smallest number L such that x is contained in the convex body. So we can calculate Lx explicitly by the following. It's still the maximum of these two functions, and it still looks like in the left side it has slope 0, and in the right hand side it has slope 1. So we can also relate the map LU to a sequence of basis vectors of Zn such that for in each linear segment there exists some xj equals lj. And here is the definition of convex of mesh delta in 2x2 matrix case. In condition 1, it's just the same with the previous one. And the condition 2, in the first, we also require ki is less than li as before. And we need another restriction here, which is ki is less than ji, because it can be viewed in the proof, and this restriction, I think, is necessary. In condition 3, it means that in each linear segment, there are two functions with slope 1 and two functions with slope 0. Then we do the same thing with just connect these nodes and define the rigid 2x2 system with mesh delta. Here is here I add another two index, which is mi and ji. In previous one, ki means in the left side of aki, the slope is 0, and the right side is slope 1. And li means in the left side, the slope is 1, and the right side, the slope is 0. But in 2x2 matrix case, we find that, for example, in this part, in step 2, here we can find that k1 equals 1 here, and k2 equals L1 equals 4 here. And when we note the A31, the node A31, we find that in left and the right hand side, the slope are both 1. So we denote this index with J1. And M1 is in the left and right side, the slope are both 0. So we can give this in each step we can denote 4 index to denote the properties of each nodes. Here is a figure of rigid 2x2 system.
And what does M?
M
mean?
means
What is?
M means in the left and right side, the slope are both 0.
So basically M, okay, makes sense.
Yes.
Can you go again to one slide back?
Okay.
This is just a definition. So you change
Yes.
two elements of the a vector into two
Yes.
ones.
Yes.
So K,
And
Ki and Gi are the ones for which the slope is 1. And
Yes, in the
we
right
start
side,
with
Ki.
Ki and Ji. We start.
and
Yes.
then where they on I want just to connect it with the next step, with the step I plus 1. So do we know something, do we have some relation between the points where these slope 1 lines arrive at and where the next slope 1 lines start from? So do we control somehow if these
No.
lines arrive to Ki, a Ki or a Ji or something?
No, we can't say that we will from Ki to Li plus 1 because in some case it may start from Ji and in the next step Ji becomes Li plus 1.
I see. So it can be, but it cannot become M.
Yes,
wait.
because
And that's also why we need L.
yes,
Okay.
L
And can you show the definition of L and M? I mean the one slide before. Okay.
Oh yes, yes. Let us look into details of this because there are all the conditions are gathered at this slide. So increasing. K and so what happens? K and J are the initial indices. M and L, or on the contrary, M and L here are initial.
yes,
M and L are initial. K and
K and J will
K and
increasing.
J, yes.
So K and J, we start with slope 1 from them, and we arrive at L and J.
Yes.
We don't know if K arrives at L and J arrives at J, or if K arrives at J and J arrives at L. So we don't.
Yes.
We have two options.
Yes.
And we also
exactly.
have two options for L and M, because
Yes,
M can
yes.
arrive to K or M can arrive to M, and L can arrive to basically the remaining one.
Yes.
Okay. So each time we have 2 by 2. Each time we have 4 options basically of how the next step points are enumerated.
Yes.
I
Okay.
didn't understand well. Sorry. I'm sorry if you
So
can repeat.
So you have in C3, look at C3.
Yes.
So you have 2 pairs of points, ML and KJ. First is the pair M and L. So the pair M and L, you can draw 2 points on the vertical line. What happens with these points AM and AL at the step I? You have these 2 points, and from both of them, you start the line that's horizontal. From M and from L. You start the line that is horizontal.
Okay.
Then you arrive at two same points after on the next step. And these two next points have indices k, I plus 1, and m, I plus 1.
Okay.
We do not know if AMI is equal to AKI plus 1 or if AMI is equal to AMI plus 1. So
But you said that we consider two lines from AM and AL which are horizontal.
Yes.
Yes.
And we do not know how so our freedom here is either that they are equal as vectors, these two, or if we need to read it from, I don't know how to easily express it, but to change the order.
To switch
the order in one of them and to keep the order in the other.
I do not understand well. If we go with horizontal lines from the MAI, LML, LA.
So let's fix AMI. We are speaking about AMI. We start with the horizontal line and reach the same point. Now the same point on the next step will be called either AM I plus 1 or AK I plus 1. There are two options for it.
Yes.
If we called it AK I plus 1 and then we start our new horizontal line from ALI, then it arrives to the remaining one, which is AM I plus 1. If we started from AMI and arrive to AKI plus 1, then we start another horizontal line from ALI and arrive at AMI plus 1. So that's, if you fix AMI and ALI, as a corollary, we have two versions of how to call this pair of points on the next step. We call them AK and AM on the next step, but we don't know which of them is K and which of them is M. And these two options are both fine for us, for the construction. And
Yes.
for the other pair of points, K and J, the same happens, but instead of horizontal lines, we draw the lines with slope 1. And while we draw these lines with slope 1, of course, they can intersect some of the horizontal lines, maybe intersect both of the horizontal lines.
You mean the difference is if they do intersect or if they do not intersect?
No. The difference is,
I mean,
this is separate.
In what case we call the I plus 1 points KM or not? So it depends on.
It depends on the next step. It depends on what happens on the next step. If they become so their role is on the left-hand side.
I understand. From M and L, we have horizontal lines, and from K and J, we have lines with slope 1.
Yes, and the one with
this notation is just to explain what is continued by horizontal line and what is continued by a line with slope 1 and nothing else.
Yes.
Oh, okay. Everything is clear. Yes.
Because in step I, we cannot determine what will happen in step I plus 1. So I just wrote these two columns.
There are several opportunities.
Yes.
And I guess if we were considering not 2 by 2 matches, but like 3 by 3 or 3 by 2, then we will have even more. So that's where it becomes difficult, right?
Yes.
Because we can say that, okay, it goes up, then it goes up one more time, but it cannot go up again because it's already the top line. And in the other case, we would have all the opportunities, as many as the dimension of something, n or m. Okay.
Okay.
Here is a example of rigid 2 times 2 system.
Okay.
Yeah, in each
Oh,
linear
we missed. I'm
segment.
sorry. I missed where in this formulation while discussing the annotation. I missed where in the formulation this peak value condition. Peak value condition. Can you go back? We just discussed. I'm sorry. I was thinking about C3 and peak. Where is here peak value?
Yeah,
It's just
it's
C2.
C2.
yes. And I found that the condition Ki
K and yes because K correspond to valley and L correspond to peak. Yes. Oh, something wrong. Something wrong. You mean we cannot hear you again?
oh
Okay.
He was
Okay.
not
can you
speaking, I guess.
yeah,
we can hear. We can.
We can. Now we can.
I want to mention I don't know the condition Ki is less than Ji is natural condition, because in construction I need this condition, but I'm not sure for general.
So you think so C2 is stronger than peak value? Peak value.
Yes, I think. In my previous thought, I think I in C2, I only need to restrict Ki is less than Li, but in the construction, I found Ki is less than Gi is necessary. I don't know this condition is natural or not.
Oh, this is some additional condition, and it may be just technical one. It is not clear.
Yes, yes, and I found that we can actually we didn't need this condition in each step. I think in the proof we only need that we have infinitely many I such that Ki is less than Gi is enough. We don't need it holds on every step I.
Just one question. Can you give an example of a local behavior of this function which do satisfy C2 with this new J condition and which do not satisfy? Just an example, maybe a picture.
I think this condition if Ki is larger than Gi, it can it's natural because if I put here in the second line, we put it in behind behind
So this
the
is the second line. This is the second line, which I put
Yeah.
now in green. Yes.
yes
So
then
in this picture, your C2 condition is satisfied, isn't it?
yes.
Yes. And how change this picture to make the condition this new condition not valid?
We can put the third line, the third slope one line to the
Below
below below the fourth line.
below the fourth, not below the third.
No, the third slope one line below the third line.
So this, if you draw something like this, if you draw something like this, yes?
No, I mean, we put the A20, this side,
Oh,
this
sorry.
point.
Can you draw this? This or I can do it. I can do it if you can. If you say what I should do.
Oh, sorry. I mean,
So
we
we
can
deal
put
with this A3. We deal with this A3. Yes.
A2.
We change A2. We change A2. This
Yes,
A2. This A2.
put,
This. Yes.
put A2 to the below of A10.
Here. Yes.
Yes.
And then where it will have jump. Oh, sorry, not perfect. Where at what?
Maybe I will.
You can do it by yourself. Yeah.
No, I think
But I
because
can.
I'm using the computer, I can't draw in the.
But you see, I can draw on the screen. So you take this A2,
Yes.
and you put it below A0.
Yes. Yes. And
then it should have coefficient 1.
Yes.
And where will be the jump? So here is the jump.
Maybe I should put A10 here.
I guess the bad condition is when you start from under A10, and at the level when we have the second, when we have I equal 1, it still does not reach A11.
But it should.
And then it goes horizontally. Then this is the condition that this is a situation when this condition fails.
So from what point it goes? From this point, I don't know, or from that one?
Wait. No. Where is... I wonder if I can draw here.
Vasya, you can try. You can try. I delete everything.
I don't see...
Can
I
you
don't have rights here.
I don't know how, but...
Oh, I probably do. Wait, I do.
Oh, great.
So let's have something like this.
Yes.
Okay.
And then
it is very,
something
very
like
low.
this. Yes. So, and then we have 2 of the slope 1, so we have this. So if we add this and instead we erase this line.
This is not good. This is peak value condition here is not satisfied.
No.
Yes.
Yes. Because the line from A20 to A31 is slope 1, so we just put a slope 1 function here. We don't
from
have
A20 to A3 has slope 1. Yeah, we have to put slope 1 here, right?
Yes, and
we
because
have to put,
A31 to
after A31 also we had to put slope 1.
Yes.
No. Because
We
here we had slope 0, so we still have to put... Oh, right. Yes.
No.
This is not good. This is not good. This is not.
Yes. I cannot... Oh, I can erase something. It works with a delay, so I can't.
We can put the whole segment A20 to A4 to... We put the full segment to the below the first line.
So do you mean... Wait. Let me try, and you will tell me if I'm
try. Please try.
So do you mean this? By full segment?
Yes.
So we erase, now we ignore this part, right?
Yes, but you should put it higher than A12. It should it should be here.
So it should be...
It should be something like this, isn't it?
But
Yes,
it should
yes,
be
because we now we
yes,
do not
exactly.
have
yeah,
this,
right.
Yes,
because now we do not
yes,
have this. We
Yes,
do
yes.
not have this, then we do not have this peak value contradiction. We have peak value only here
yes,
in this new. So, and such a construction satisfies template condition, isn't it?
yes,
But you
yes.
cannot, but you yourself cannot cannot work with it.
Actually, I can because here in step 2, I can adjust the GI vector GI, but in step 3, we find that GI is larger than KI. So some error here I can deal with in step 3.
But we cannot deal with it if it repeats infinitely many times and the distances are unbounded, right?
Yes, so I think I need the condition that for ki is less than gi is an infinite set. If it is finite, I think this construction will fail.
So but that's basically the idea, because we say that it's equivalent up to a finite difference. We can just ignore the ones.
Yes, we can ignore finite part.
Yeah.
The
Yes.
finite part.
So basically this condition is good because these templates with these restrictions are enough to give us all the 2x2 matrices in this correspondence, and the remaining ones can work or can fail, but we don't really need them, because even if they do work, they actually themselves up to a finite difference corresponded to the template of this form, so it kind of spoils the bijection for us.
I do not understand this. I do not understand this. So
well, it doesn't spoil the bijection actually.
I do not understand. You have excluded, so I do not understand what Vasya said, because in your condition, in your definition of template, you just exclude this case what we have drawn now, isn't it?
For simple, I think I didn't need I didn't need this restriction, but for simple
Am I right that you do not need this restriction locally, but this restriction globally verifies that nothing goes wrong?
Yes.
So
yes.
what if we have one part of the template, or how it's called, mesh, something with mesh.
Okay, with mesh.
If we have one part of this, I forgot, canvas, it's called canvas. If we have one part of this canvas that goes wrong, and then everything else, starting from step number 3, for example, satisfies Eumen's condition, then this is up to a finite difference is equivalent to the canvas that completely satisfied the Eumen condition, right?
Yes.
Actually, it doesn't matter at all what this part is, because if it starts to satisfy conditions starting from step 3, then no matter what happens at the first step, it's still up to finite difference, can be adjusted to satisfy Eumen's condition.
I still do not understand. If we have a template which has infinitely many times this pattern, which we have.
If it's the exact copy of this pattern, it's still fine, because if it's the exact copy with the same distances. The bad situation is if you have similar combinatorial pictures, but with higher, with bigger and bigger distances.
Yes, I meant just something like this.
Then it spoils the game, because no matter how big is the constant that you shifted by, you still not how big is the freedom that you allow for this error, it does not cover, so there will be some step where the difference between the corresponding functions on some of the levels is bigger than this error. And then it means that it does not satisfy to, it does not correspond to any metrics up to a finite perturbation, finite change. So we decide to restrict ourselves and not to allow these conditions at all, because we don't really need them anyway. And by restriction like this, we do not lose anything. We do not need them because if we have infinitely many times this situation, but the distances do not grow up to a finite perturbation, up to a finite error, bounded error, it corresponds to the canvas that completely satisfied this condition. And if it does not correspond to a template that completely satisfies this condition, then the theorem, as I understand, says that we do not have a matrix.
Because the last sentence I do not understand. Why, if this we have a picture which is similar to that, but when all the distances are growing, why in this case we do not have a matrix?
I mean, I understand that it's Yumin's proof, that the Yumin statement that she just proved. I don't know why, but
isn't it? Is it so?
I mean, for example, in this picture, in step 2, we can in step 2 we have some error here, because of we didn't have the condition Gi is larger than Ki. So this will cause some error. But when we keep this error and do the next step, if the next step Gi is larger than Ki. So in step 3, I can cancel the error caused in the previous step. So I mean, if Ki is if Gi is larger than Ki fails in some step, but finally it will hold in some step, then I can cancel the previous error. So I think this just needs to happen for infinitely times.
Okay, so you mean so if this situation we draw here happens for infinitely many times, then you cannot apply your proposition, your statement.
Yes.
And
but
are there real examples of matrices for which these situations happens infinitely many times? Do you know?
I conjecture that if Ki always larger than Gi, it will cause some disconnected graph, but I didn't prove that.
Okay. So
I think it will have some relation.
I see. So I think, Vasya, you are not completely right, because you mean cannot do this situation when this picture appears infinitely many times, and maybe something hidden there, maybe some connection problems are hidden there. So very interesting. So this is very interesting. And if it happens only finitely many times, I agree, you can forget about the beginning, because everything in the beginning is on the bounded distance. You take a larger constant and everything in the beginning disappears. Excellent. Thank you very much. Thank you very much for the explanation. Something became a little bit more clearer, and we may continue.
Okay.
Oh,
So
so I
just
should
a
delete.
question.
I should delete this.
Oh,
I should
So
delete. I should
so
delete everything.
here do we agree that this situation, the problem is not that it happens infinitely many times. It's when this picture becomes arbitrarily large. Because if it stays small, but it happens infinitely many times, then it's okay.
Yes.
Yeah, that's also what I meant by
Because
yes,
and
if it
I
stays
mean, if it stays small, somehow it stay like bad.
bounded distance. If it remains small, then it is bounded distance. And
Yes,
if it
yes, yes,
remains
yes.
larger and larger, your theorem doesn't work.
yeah, that's what I meant as well. Yeah.
Oh, yes,
Yeah,
yes.
yeah.
Then,
Okay.
then I
It was
understand. Then I understand.
just to be sure that we are all we all agree on the same thing.
Yes,
Okay.
yes.
Yes.
Thank you.
We cannot overcome the problem now when this picture becomes larger and larger and larger in scale.
And then the question is, does there
Because-
exist some matrix such that this picture appears with an arbitrarily large size, right?
Yes. And the conjecture is that in such a case, we lose some connection properties. Yes,
Yes, and then the question is, what does it mean if it's not connected?
I'm afraid that it means that some best approximations lie in two dimensionals of space.
Yes,
Asymptotically, eventually.
Yes.
I'm not completely sure. This is just a guess. And this means this is related to some connections, to some
Yes.
connectedness problem.
Because
Okay.
this is one of the questions I ask myself, not only for 2 by 2, but for n by m. What does it mean when we lose connectedness in these graphs? And it's not so clear to me.
It is not clear.
But this
I'm
is
sorry, it
maybe
is not
out of
clear.
the topic of today.
It is not clear for me also. Wonderful. Okay, let us continue. So we are speaking about the same thing.
Yes, perfect.
We have clarified that we are speaking about the same thing. So, okay, thank you very much. Let us continue. Wonderful.
okay. I
Very
also want to I also want to mention that if this graph is not connected, then it can be divided into two connected parts. And a theorem given by Schmidt and Zumira said, if this graph can be divided into two parts, then we can construct a vector u in each part. So I think the theorem still true, because we can from one part we can construct some vector u, and in another part we can construct another vector u2. Then we put it together. Then these two map LU1 and LU2 will match this graph. I think it's a theorem given by Schmidt and Zumira. I didn't I'm not quite sure about this.
Okay, let us continue.
Okay.
So this is the
So
theorem under under your additional condition.
yes. So for a given rigid 2 times 2 system, we can construct a two-dimensional subspace U such that PT minus UT is bounded by this constant.
Okay, so the formulation is rather clear.
Yeah, the formulation is clear, but we say that D is greater than 16E squared.
Yes.
And it exists. and we are
yes.
before this we're given P. Does it mean that the bound is not uniform for different
Oh,
P?
Uh,
Because D is greater than if
uh,
it
on what? D depends.
I think D depends on the dimension. D only depends on the dimension.
It doesn't depend on P.
So we
It
can
doesn't
so
depend on P.
oh yeah.
D is a constant. Oh, sorry.
I see.
Here. For
So
every
we can
P,
say there exists D such that for every P.
yes. For every P, there exists some
Oh,
constant.
that's so it's uniform.
Yes.
But
D
you
only
cannot.
depends on
Is it
dimension.
possible to give upper bound for D? Lower bound is not so interesting indeed, as mentioned, Vasa.
I will check later. I'm not. I can't remember the
Okay.
But at least it exists. It's
Yes.
uniform. So it
And does it depend on delta?
It doesn't depend on delta.
It doesn't depend on delta.
But delta needs to be larger than the log of.
Yes.
yes.
But it would be reasonable to have here an upper bound for D. I do not
Yes.
want to. I do not insist to have it immediately. I do not want you to write immediately. But in general, it is reasonable here to have an upper bound for D.
I think because in the construction we use the induction theory. I will begin with the initial choice of basis of vector. So I need to choose some D. So I think D is a constant. We can choose any constant just larger than 16 e to the power of
Maybe
2.
maybe the formulation is that not there existed, but for any D such as is
larger than.
yes. Maybe this
yes,
they exist. They exist is not good. So maybe here instead of they exist, you should write for any D. So it is not completely clear now. Okay.
I will check it later.
Okay. Wonderful. Okay, so let's continue.
Oh, okay. So I want to say something about the proof. Here I want use the induction theory. So I will begin with a basis of Z2 satisfies the following condition. For a given rigid 2 times 2 system, we let capital A equals e to the power of A. And in step 0, I begin with these 4 vectors satisfies the following 3 conditions. 1 is the norm condition, and 2 is we need the vector respect to AM0 and AL0 is almost orthogonal. Then these 2 vectors will form a subspace, 2-dimensional subspace in R4, and here the W0 is considered as the base space. Then I need the other 2 vector, the projection to the orthogonal subspace of W0 have the following 2 conditions. if we together with the condition 3 and condition 1, we can calculate the Lxj function with respect to W0. The Lx function is what we defined before.
So
It's in
one question
here.
about these three conditions. So
Mhm.
look, is it true that the third condition means that if we have W, we have an orthogonal subspace to W, and the third condition means that if we project the vectors which are not in W, then the length of the projection will be almost the same as the length of vectors. Up to some constants. Yes?
Yes.
Okay,
Yes.
okay.
Because the definition of function Lx consists of two parts. One is the norm of vector, and the other part is the projection to a two-dimensional subspace. So if we together with condition 1 and condition 2, we can draw the Lx x function. We find that it will approximate the segment, the first linear segment very well. For example, if we consider the x4 here, x4 is defined by the maximum of log x4 and t plus the projection of x4 to the subspace of the orthogonal subspace to W0. Then both this side can be bound by some constant plus A4. So Lx will match the first segment very well. In each step, I want to construct a basis satisfies the following three properties. Then because in each step we construct a Wi. Finally, I will prove that the sequence of Wi is a Cauchy sequence, and it will eventually converge to a subspace W we called. Then we find that because the difference from Wi to W is very small, so each vector xi correspond to the final correspond to the subspace W is very close to the previous function. So we'll approximate this rigid system very well.
So your general logic, just to be sure that I understand, is that we take this canvas on each new step, each new section of this canvas. You basically by all this technical thing, you correlate it to a subspace. You correlate it to two-dimensional subspace, and two-dimensional subspaces, as you showed us earlier, you have a bijection with matrices for almost all in this chart. So you basically now to any new step, any new let's say we go with step delta or with step proportional to delta, to any point in time of the format something multiplied by delta, or maybe to some of them, we attach a matrix, and the theorem is that this sequence of matrices converges, and the matrix that is in the bijection with the whole canvas is the limit of this sequence of matrices. Okay.
So in each step, we need to construct a basis of Z4 satisfy the following condition.
But these bases, each of these bases should be close to, should have the vector of else close to template in the time when
Yes.
this is
for each-
additional condition. This is what you have presented on the slide. This is a technical condition. What basis do you construct? And all in addition, you should have a condition to be close to template, isn't it?
Yes, the condition 1 and condition 4, these two conditions will imply that for each LXK match will approximate the template very well.
Here in your slide, condition 1 and condition 4 give
Yes.
this approximation property. Yes?
Yes.
Okay.
Yes, and one special is for xji is a slope 1 vector, and we don't need xji satisfy the condition 1. We just need to let xji satisfy the condition 2. And the condition 5 is we want to prove that the sequence of Wi is a Cauchy sequence.
And one more question. At each step, you replace just one vector from the previous step.
No, I need to replace two vectors.
You replace two vectors.
Yes, in Roa's proof, he only replaced one vector. But in this case, we have two slope 1 function, so we need to change two vectors.
Okay.
For concrete construction, in Roa's proof, in each step he changed the vector he changed the vector xli, and in our proof we need to change xli and xji. Construct the vector xli, I use the same method given by Roa, and the only new idea, the new idea comes when we construct the vector xji, because in Roa's setting, for example, n equals 4, the subspace W is 3-dimensional. So so he only need to project xli to a 3-dimensional subspace. But in 2x2 matrix case, he need to project not only xli but lji. So if we from step 0 to step 1, the base space changed from W0 to W1. So if we use the previous xj0, then we can use the triangular equality to calculate the error caused by the change of space, which is the distance between W0 and W1 times the norm of x2. It can be bounded by by the by this constant, but we don't want we don't want this arrow at in each step, so we need to adjust the xji vector. This slide I want to show how to construct the new vector. We can consider a chain of subspace. W1 is defined by the two horizontal line vector, and Vi is we put xki to W1, and U is the whole subspace, is the whole R4. Then we can choose the unit vectors U and V such that UV is an orthogonal basis of the orthogonal subspace of W1 to R4. Then we can project the previous ji minus 1 vector. Here is x2. We put x2, project x2 to the orthogonal subspace of Wi. Here is some c times u. This c we can calculate it concretely. Then for each b, we have cu minus x2 plus bu. This vector will lies in the subspace V because the definition of cu minus xv must have projection. If we project cu minus x2 to the projection of the orthogonal subspace of V, it equals 0, and the vector V lies in the subspace of V. So we can rewrite this vector by the basis of V. So we have this equality for some C1, C2, C3. Then we project this vector to the orthogonal subspace of W1. We will get CB plus CU plus BV minus the projection equals to just C1 times the xk1 projected to the orthogonal subspace, because xm1 and L1 lies in the subspace W1. So if we let WG1 equals x2 plus C1 times xk1, then the projection have an upper bound by C plus B plus the projection. And the projection of xk1 to the orthogonal subspace of W1 is we can calculate it concretely by condition 4. And if we restrict Ki is less than Ji, then the value of this projection is much smaller than AJI. So we can choose a proper B such that C plus B plus this projection is less than some constant times AJI. So this construction will will construct a proper vector xji such that the condition 4.
Okay, okay.
Yes, I need probably to separately read it and think about it for longer to understand what
Yes,
exactly is
yes,
going
I
on.
agree. Too many formulas on one
It's
slide. We cannot understand just
the
very
last two
Yes.
slides I cannot digest. I understand very, very generally what you're trying to achieve, and I understand that you can do it generally this way, but I
So these conditions about
stopped understanding what indices mean at some point.
roughly speaking, this conjunction about angles and projections gives enough space to find some next vectors because we have enough space. So this is some more precise formulas. What
Yeah, this is as much as I understand as well.
Okay, of course, more precise formulas need more detailed consideration, not during the lecture. That's why, by the way, I think that this recording may be important for people. Okay, so we may continue.
Oh, okay. So the next slide, I just
Oh,
talk
this is
about
important explanation because this is a condition. This is something about new condition. Yes.
Yes. I think the why we need that Gi is larger than Ki, we can see in the previous slides. When we calculate the upper bound, we use the xgi projects to a subspace, and this projection can be bounded by, because we restrict this projection in condition 4. This projection is bounded by some constant times AKI, and we need the xgi to the subspace, project to the subspace is bounded by AGI. So if Ki is less than Gi, then the previous so in the first part of the arrow is much smaller than D plus AGI. So we can choose some proper B such that CB plus this projection is less than D times AGI. So we need to restrict Ki is less than Gi. But if Ki is larger than Gi, we can we didn't use this construction, and we just use the previous xgi minus 1. This slide calculates that if we use the previous vector and don't change it, here is some arrow, but we can memory this arrow to the next step. Then if in the next step Ki is less than Gi, we can use the same argument to cancel this arrow. That was I want to explain here, that we need is the condition I such that Gi is larger than Ki being of infinite set.
You claim that if sometimes the condition Ji is less than Ki is forbidden.
Yeah.
For your theorem, it is forbidden.
Yeah. Is forbidden.
You say
it's only forbidden for this to happen always starting from some point?
This is just the question. So if you have a condition, this condition somewhere, then up to this you have some error, and this condition
Yes.
enables to kill this error.
Yes. Yes.
At
If
this step. So if you have some error which becomes larger and larger, then not completely clear, because error may be large enough. Why it is uniformly bounded?
because when we met some I this I is ji larger than ki, then we use this argument.
Yeah, so I understand that if we meet, let's say, I1 and I2, and for both of them the condition is satisfied, but between them there are some other i's where it is not satisfied, potentially. So I also don't understand this part, because in my understanding, okay, let's suppose that I1 and I2 are very far from each other. So in this meantime, they have a very big error, then this error resolves again, so that there is zero error. But in the middle between these I1 and I2, the error is very big, and we can have these patterns again and again, so that this middle error grows and grows. So I don't understand how this correlates to the uniform bound for the constant, because
yes, I can imagine lim-inf bound for the error by this argument, but uniform bound lim-inf may be reasonable, because this moment when we have j greater than k, then we can repair the error, but we can do it locally.
But if we consider only lim-inf, it's not clear why we have correspondence to a unique matrix. Maybe there is lim-inf at one sequence of points of the errors is zero, and lim-inf or bounded, and lim-inf for the other sequence of points of error compared to the other matrix is also bounded, but these matrices are different. So this is what I don't really understand. Isn't it that maybe somewhere in the meantime we will have another sequence of, technically we need something to construct this example, we will have a sequence of another sequence of points along which we have a correspondence to a different matrix?
Because in each step, actually we are construct a subspace. No matter gi is larger than ki or not, the subspace we construct is always a Cauchy sequence.
Okay, so Cauchy sequence still holds.
Yes,
okay,
yes. It just affect the xgi's, the value around xgi. It doesn't affect the distance between wi and wi minus 1 or wi plus 1.
Okay, I think probably we need to understand the construction better and to actually read the formulas.
Yeah, the
I
condition.
think it is difficult to understand this comment without understanding the construction.
Looks like
this is the question to Vasya.
I think so, but
Okay.
So as far as I understand, the fact that this extra condition appears infinitely many times, this just makes sure that we stay connected, right? Because if it doesn't happen anymore, then we are disconnected, and probably we lie in two different subspaces. But then, if it's connected, I don't see why it would not be possible that this picture that we want to avoid appears at larger and larger scale. This is what I don't understand. But probably I would need to understand also all the technical details that I didn't get yet. Because maybe it's not very clear what I explained, but if we don't have this extra condition anymore at some point, I think it's quite clear that we are disconnected.
Yeah.
And if we have it infinitely many times, between 2 times, I don't see why this forbidden picture could not happen at an arbitrarily large scale, which is what we want to avoid to keep a uniform bound.
Maybe I'm not quite sure about the last statement in my slides.
Okay.
I think in this these 5 conditions, condition 1, 2, 3, and 5 is without condition 1, condition 3, and condition 5 didn't depend on the choice of xji. So no matter we change xji or not, it doesn't affect condition 1, 3, and 5. So we can always construct a Cauchy sequence of subspaces. But if we don't change xji, then in each step construction we will cause some error, and this error will add. And I think it's not a uniform constant. But when ki is larger than when ki is less than ji, we can use a method to cancel this error
Yes.
caused
Okay.
before. Such that xgi satisfies the condition 4.
Okay.
If xgi satisfy condition 4, then for the final w, the Lxgi function the final xgi function will the bounded between Lxgi and the graph the rigid system can be bound by the constant of D here. Because condition 4 and condition 2 together will guarantee the Lxgi function with respect to wi is bounded difference with the rigid system, and because wi distance between wi and w is very small because it's a Cauchy sequence, so the Lxgi function with respect to w will have bounded difference with the rigid system.
Okay, I will have to look back at our video and think again about this. Thank you for your precisions.
Okay, thank you for listening.
Oh, thank you very much. So we are coming to the end, yes?
Yes. just
Oh,
the conference
okay.
reference.
Oh,
and
thank you very much. Thank you very much. It is indeed a very interesting and very important talk.
Yes, it's.
Thank you very much.
Thank
I
you.
think it's impossible to understand proofs today, but it's possible to understand what's going on, and I guess
Yes,
it's
yes.
a big success
And indeed,
for us.
that
Yes.
there is a problem related to connectedness, possibly related to connectedness. It is very interesting because I have a feeling that something like this should be in this situation.
Yes, and maybe in the case 2 by 2, being not connected is not too difficult to understand in terms of being in two different subspaces. But maybe for arbitrary m and n, this is more tricky.
I'm sorry. I think that in 2 by 2 it is not the easiest case. I think the easiest case is 2 by 3, where indeed there are there is possible disconnectedness, and there should be some curious examples.
Okay.
As a specialist in degeneracy of dimension, I can
Yes.
suggest something like this.
But I think this is there are very interesting questions to ask in terms of connectedness of the graphs. What does it mean? And to understand this, it's very important to understand the construction that human is trying to do right now.
By the way, a few days ago, I get a message from Damien where he wrote that he will finish a paper with River Cookie, and there he has a curious example in approximation of a point in R4 by three-dimensional subspaces.
Yeah,
I don't know what does it mean.
He also sent me an email about this paper, and I didn't have time to check yet. But I think there is something interesting.
Yes.
There's some strange and unexpected behavior.
Yes. I have a lot of things. Let us finish the recording.